right, as we get started, want to take a look at your homework. You had just one equation that you needed to graph, and what shape is this and how do we know? Jamie?
It's a circle.
How do we know?
Because both the x and y are squared.
Good, we got both of them squared and added together, so we know it's a circle. And with a circle, there's two things we have to know, class. Center and radius, right? It's defined as the locus of points having a given distance or radius from a given point or center. And so we need to get it into the center radius form or the circle form. And Quentin, how do we do that?
You would put your x's together, so x squared plus 2x, and leave a blank, and plus y squared minus 8y plus blank, and then equals negative.
There we go. And what do we put in these blanks? You're right, they are both plus blanks, aren't they, Jamie?
We put a 1 and a 16.
Good, a 1 and a 16, half and square, remember. And what we put on one side, though, so if I'm going to put a 1 and a 16 on the left, I also need to put 17 on the right. So we're going to take these two perfect square trinomials we completed, turn them both into, what are the two binomial squares, Jamie?
S plus 1 squared, y minus 4 squared.
And of course, on the right-hand side, Quentin, we just have a 9. So from here, we can tell that the center of our circle, Quentin, should be
negative 1, 4.
And then the radius is going to be 3. All right, so to graph it, we should have taken our, marked our center point, backward 1, upward 4, and then take your compass out and measure it out 3 units. So whether it be 3 units over, up, down, doesn't really matter. And should be able to put a little circle. Easier said than done, apparently. Right about there. Should have had something like that for our homework. Any questions on the circle? Just want to make sure we keep that sharp. And then remember the parabola. We just took a quiz over it, so it should be pretty fresh in our mind. But the difference in the conic form between the circle and the parabola, Quentin?
Only one of the x's or y squared.
Right, only one of these things is going to be squared. So for instance, maybe the x squared disappears. Well, that would tell us, well, probably the plus wouldn't be there either. And so that would tell us, okay, this is going to be a parabola instead. And remember, there's really 2 key things that define the parabola. As we talked about at the end of our last lesson, 2 things that we use to find the parabola. What 2 things define the parabola per its locus, Jamie?
The vertex, the vertex. And
that helps you find the equation, but what actually defines a parabola? It's the locus of points.
Equidistance from a point in a line.
Good. The point called the?
Vertex.
No. That's part of the parabola. Equidistant from a point called the focus and a line called the directrix. Now, neither of those actually shows up in the equation directly, right? We extrapolate them from the equation. So what are the 2 things we needed from the equation?
The vertex and the focal length.
Good, vertex and focal length. If you can find vertex and focal length, you can get the equation of the parabola. For sake of time, we won't necessarily go through those steps. We just took a quiz over that. We should be good. Let's move on in your notes then to our third conic, and that is the ellipse. Our third conic section, which is the ellipse. E-L-L-I, I'm trying to save this Cartesian plane. E-L-L-I-P-S-E. E-L-L-I-P-S-E, the ellipse. Practically speaking, when you were a little kid, it's roughly equivalent to what you called an oval back in the day. It's not quite the same thing as an oval, but very similar in that regard. Here's your definition for an ellipse. An ellipse is the locus of points having a constant sum of distances, from 2 fixed points. Locus of points having a constant sum of distances from 2 fixed points. Unlike the circle that has a constant distance singular from 1 fixed point, the ellipse has a sum of distances from 2 fixed points. You'll recall in physics, right? We talked about the planets going around the sun in elliptical orbits, and we said the sun is one of the fixed points, and then there's another fixed point somewhere in space, just an empty point in space, and at every point in the elliptical orbit, the planet is the same sum of distances. So you'd have to add the two distances together, and that sum never changes. In your textbooks, if you look at page 244, how to actually draw an ellipse. The suggestion was, using a cork board here, put a couple of thumbtacks down and tie a string to the two thumbtacks. Put the pencil in the string and pull it tight. And as you go around, and you're probably going to end up doing half on one side and half on the other so it doesn't get the string twisted, but it'll give you that, if you keep the string tight the whole way, it'll keep the sum of the two distances the same all the way around. And it'll give you that ellipse. So those 2 points, by the way, are called the foci. If you put that in parentheses after the word point, it's called the foci. That's the plural of focus. One focus, two foci. Like an alumnus, alumni, you're both about to be alumni in about 7 weeks. Quinn's a big smile. I can see it through the mask. Big smile. Oh, yeah. Means I graduated. Hey, just got a couple more pre-cal tests to pass. We got it. Just kidding. All right, so a foci. So with our ellipse, let me just draw, again, what we would normally think of as an oval. And of course, with an oval then, it's either going to be longer than it is tall, or wider than it is tall, or taller than it is wide. I kind of drew it at a bit of an angle here, but we understand there's going to be a point here at the end where it begins to change direction, and exactly on the opposite side there will be kind of the same thing. And that goes to the wide ends, all right? Where it gets tall or long, it doesn't really go to a point, it almost straight lines. Not quite straight lines, but close to it. If we were to run a line through these 2 points, we could refer to this line as the major axis of symmetry. The major axis of symmetry. You realize a perfect ellipse, then, you could spin around this line. It's going to be the same on both sides. But what makes an ellipse unique is if you were to find the midpoint between those two ends, you could draw another line perpendicular to the first, and these two sides would be mirrored of each other as well. We could call this line perpendicular to the major axis of symmetry through its midpoint, the minor axis of symmetry. It's symmetric 2 different ways. Now in our case, we've got this thing slanted on purpose, but you understand our ellipses that we're going to draw are either going to have this oriented so that the x is the major and the y is the minor, or the y is the major and the x is the minor, okay? Which you might recall, anytime we saw ellipses before, when we answered the question of symmetry was, is it symmetric to the x-axis? Yes. Y-axis? Yes. Origin? Yes. It was symmetric to everything, remember, with these ellipses. These 2 points here are called the vertices. We'll label them V and V prime. So 2 vertices in an ellipse, 2 vertices in an ellipse. And this point that's at the very middle, by the way, it's at the middle of both axes. This is the midpoint of both the major axis between V and V prime and this minor axis length is called the center. So just like a circle has a center, an ellipse has a center. The difference is the points aren't always the same distance from the center, but there is a true center point. Somewhere along here, you will see those 2 points that the sum of the distances stays the same. These are called the foci, and they are along the major axis of symmetry. So the major axis of symmetry runs through the vertices, the foci, and the center. The minor axis of symmetry is the perpendicular bisector of the VV prime line. By the way, there are also 2 directrices. A directrix out here, and a directrix out here. For our purposes, they don't really serve much of a purpose. So we're not going to actually graph the directrices, but they are there technically. There are also 2 latera recta, a latus rectum through one focal point, and a latus rectum through the other. Collectively, the plural is latera recta. So you'll see 2 latera recta. Now, the major axis of symmetry is this axis, but specifically, the length from V to V prime, we'd say the length or the height, depending on the way it's oriented, of the ellipse is actually referred to as the major axis itself. The major axis goes from V to v prime. And then although we could refer to this line as the minor axis of symmetry, the actual minor axis itself is thought of as just from the top to the bottom, or from the side to the side. If we wanted to give these points names, we could call these A and B, for instance, and that would be the length of the minor axis. Just goes from top to bottom, or if it's a tall ellipse, from side to side, the width or the height. The other dimension that ain't been used yet, right? So VV prime will either be length or height, or width or height rather. The minor axis is the other one of those, okay? And that just measures across the ellipse. So several points here on the ellipse. Again, we've got our vertices, we have our foci, we have the center, we have latera recta that are going to be drawn through the focal points. We have a major axis, minor axis, a lot of different parts to know here. A couple of length definitions I want to give you here. Let me draw a ellipse this way here. So again, we could draw a line right through here. That would be our major axis, VV prime. And we could draw the perpendicular bisector, and this would be our minor axis. If we were to look at this length from one vertex to the center point, vertex to center could be represented by the little letter A. Well, obviously, since it's perfectly symmetric, C to the other vertex is also A. So we would say that the length of the major axis is 2A. So I will algebraically represent that. We could represent from the center up to one of the end of the minor axis as B, and of course from the center to the other end of the minor axis as B. So the length of the minor axis is 2B. We'll spare the joke. All right, so 2B is the length of the minor axis. Again, you're going to have focal points or foci along here. This distance from focus to center, and again, it's going to be the same on both sides, is represented by the little letter C. So the focal length is represented C. So we're using these lowercase letters to represent different lengths within the ellipse. C is the focal length. Now, coming back here to the last ellipse that we drew, that means this length here is C. This length here is A. But I want you to think about this for just a moment. This point here has also this length A, but if I were to translate to this point, it would also be A. And this length here could be B. Okay, so this, as it flattens out, would end up becoming A again. All right, so if we wanted to find the length of C, C can be found by taking the square root of A squared minus B squared using Pythagorean theorem. So put a star next to this, make sure you have this in your notes. To find focal length, we're going to take the square root of the A squared minus the B squared. Square root of A squared minus B squared. Square root of A squared minus B squared is your focal length. And then for the latera recta here, the length of the lattice rectum is going to be 2B squared over A. 2B squared over A. And therefore each side from the focus up to L or focus to R, right, each side would be half of that, which would simply be B squared over A. So put a star next to that. For the half lattice rectum, or half latera recta, going in the plural sense, B squared over A is how we'll calculate that. Now remember, we said that for every conic it has a certain uniqueness to it. We understand you could have an ellipse that's nearly circular, or you can have an ellipse that's really long and thin. So because ellipses don't always have to have, now again, I know the parabola didn't always have the same shape. It could be narrow or wider, but the ratio of distances was always consistent. And therefore that ratio always gave us an eccentricity of 1. For the ellipse, the eccentricity is going to be calculated by comparing the length of half the major axis to this focal length, or rather focal length to half the major axis. Well, since the focal length always falls inside the half major axis, when we make the ratio C over A, it's always going to be a proper fraction, or therefore eccentricity always is going to be less than 1, between 0 and 1. So to find eccentricity, we're going to make the ratio C over A, focal length to half major axis, and therefore the eccentricity always will be between 0 and 1. Now imagine for a moment if the foci came in closer together. Well, that's going to happen if the ellipse is nearly circular. Your foci will be very close to the center. And for a perfect circle, the foci will be on the center of the circle. Both foci will coincide. So your focal length becomes 0 if the foci were on the center. In which case you have an eccentricity of 0, therefore we'd have a perfect circle. So as foci come in, it gets more circular. As foci go out to the ends, right, very much approaching where the vertices are, you get an eccentricity closer to 1. So the eccentricity just tells you the distortion from a true circle. An ellipse that has no distortion, again, both foci on the center, eccentricity theoretically of 0, right? And then the eccentricity of 1 would occur if the foci were to come to the end, but it never quite hits that, because otherwise it'd be a circle. And it never quite gets to the end, otherwise you'd have a straight line. So you can't, that'd be a totally different conic at that point. So that's where our eccentricity falls between 0 and 1. The circle, again, always has eccentricity 0, and the parabola always has eccentricity 1. The ellipse's eccentricity falls between those values. Right? Questions on that? All right. Now, for the elliptical form, and I'm running out of chalkboard space here, so let me go to erase some of this stuff here. The form we're looking for our ellipses. Again, we had a circle form. Remember, x minus x1 squared plus y minus y1 squared equals r squared. We said for the parabola, it was x squared equals 4py, or y squared equals 4px, until we started translating the vertex. For the ellipse, so in your notes, the elliptical, that's an L, form is going to be x squared over a squared plus y squared over b squared equals 1. Or x squared over b squared plus y squared over a squared equals 1. Where a squared is greater than b squared. The elliptical form is going to be x squared over a squared plus y squared over b squared equals 1, or it's going to be x squared over b squared plus y squared over a squared equals 1. How do you tell which one it is? Well, a squared is always the bigger value. Think about it. A is always the length of the major axis, so A has to be bigger than B. If it weren't, if B were bigger, then B would be A. Okay? I know that's mind equals blown on a Monday morning. You're like, I just took tests. Sorry. All right? But A is always the bigger value, so therefore A squared is always the bigger value. Notice your key, if you write this down, is you've got to set the equation equal to 1. You've got to set the equation equal to 1. All right, I'm going to erase the stuff we're going to need in just a moment, so make sure you've got your notes handy for reference. Let me show you, don't work this with me necessarily, just follow along, and then we'll work a few of these together in just a moment. Let me show you how you're going to spot the ellipse. First of all, taking it back, x is squared, y is squared. They're both squared, they're both positive, just like a circle. But remember, a circle had matching numbers, where you could cancel them to get 1s, and an ellipse is going to have mismatched numbers. So it looks like the circle, except with mismatching numbers here. The key, again, is to set it equal to 1. So instead of equal to 225, it's got to be equal to a 1. Well, how do I get a 1 right there? Divide by 225. There we go. Divide away to 225. And of course, that gets me the 1 right here. Well, ideally, in a perfect world, you'd cancel the two values, which canceling just means you divide top and bottom by 9. Right, divide the 9 out. You have to have a plain old x squared and a plain old y squared in the top, so we're going to divide top and bottom by 9. Obviously, divide the top by 9, you get x squared. Divide 225 by 9, You can use your calculator if you need to.
25.
It is 25. And then here, we're going to divide top and bottom both by 25. So that gives us, of course, the y squared, because we needed a plain old x squared, plain old y squared in the numerator. And we divide top and bottom by 25. 225 divided by 25 is 9. It doesn't always work that these two numbers trade places in the denominator, but it happens quite often, okay? So don't assume it's always that way, but often, let's be honest, it's going to be that way. The first thing we need to know is where is the center of our ellipse going to be? And for this elliptical form, this is the form anytime the center is at 0, 0. So this is the elliptical form for a 0, 0 center, which is kind of how we started everything, didn't we? That's how we started vertex at 0, 0, center at 0, 0. Well, here the center is going to be at 0, 0 also. The next thing you've got to determine is which axis is the major axis. You need to know if this ellipse rather is going to be tall or if it's going to be wide, right? And to figure that out, you've got to figure out which one's the bigger number. Remember, A represents half the major axis. So a squared then is going to refer to the major axis. A squared is the bigger value. The bigger value here, of course, is the 25. X-axis is major. This ellipse is going to be wider than it is tall. Does that make sense? The next thing you need to figure out is the length. Of the major axis. You know what? I'm going to abbreviate major axis because I'm lazy. I'm going to abbreviate it capital M, capital A for major axis. Now this 25 is the bigger value, which means it's the A squared, right? Therefore, if 25 is A squared, then A equals 5. And the major axis, remember from your notes, always has a length of 2A. So if A is 5, the major axis is 10. 10 units wide. So this is a 10 unit wide ellipse. Another way to put that would be, however, to just take the square root and say 5 each. From the center, 5 in each direction along the x-axis. Make sense? So if I were to try to graph this, let me go yellow here. We could put the center point, C, at the 0, 0, and go over 5 to one vertex, and over 5 to the other vertex. We'll call this one V and that one V prime, just to go left to right here. The next thing we need to know is the length of the minor axis. I'm going to abbreviate this little m, little a. Capitals for major, lowercase for minor. And remember, the minor axis is 2b. I'm showing great restraint. All right, well, remember, the smaller of the values is the b squared. This is b squared, therefore b is 3. Well, 2b is the length of the major axis, so the minor axis rather, so the minor axis must have a length of 6 units. Or again, 3 each might be a better way to think of it. Well, the minor axis has to be the other one. Since x is major, y is minor. We're going to go up 3, down 3 for that total length of 6. Again, these don't get represented by any letters necessarily. It's just there they are. The next thing we need to find is where do the foci go, the focal length. And you recall focal length is represented by the letter C. But from your notes, C is equal to the square root of a squared minus b squared. So remember, the numbers you see pictured are the a squared and b squared, right? Once you get your denominators. So we're going to take bigger number minus smaller number equals, and then take the square root, 4. Now you could argue because of the because of the square root, positive and negative 4. You don't necessarily have to write it, but it is in fact positive and negative 4. From the center, you go out 4 to one focus, and over 4 the other direction to the other focus. So there's our two foci. Now notice, the foci go out 4, the vertices extend out 5. So C is 4, A is 5. Remember, the ratio of focal length to half major axis is how we find that ratio of distances. The eccentricity, right? So the eccentricity then is 4/5 or 0.8. That's pretty close to 1, right? It's closer to 1 than it is to 0. So this is closer to being a longer, flatter ellipse here. But again, if you just try to connect these dots that would be a bit of a challenge, wouldn't it? I mean, it'd be really hard not to just make like a rhombus type thing, wouldn't it? So to help us then, of course, just like for the parabola, the lattice rectum gave us the width to make it nice and curved. Well, we know the ultimate width because of the minor axis. But to help us hit the curve just right, we have the latera recta. Generally speaking, I'll ask for the half latera recta length. And the half latera recta length from your notes is?
B squared over A.
B squared over A. The whole thing 2b squared over A, but b squared over A. That means you're going to take the smaller number divided by the square root of the bigger number. Well, in that case, b squared over A is going to be 9 over 5. 9 divided by 5 is? 9/5, which is? 1 4/5, right? Now, if you wanted to, you could do it on the calculator, do 9 divided by 5, you get 1.8. I don't really care how you do it necessarily, but remember the lattice rectum length is going to go up and down perpendicular to that major axis. So I'm going to go up 1.8, down 1.8, up 1.8, down 1.8. Again, this we'll call this L and R, so L prime and R prime. Now, just like when we drew the parabola, we started at the vertex and we went through one of the at one end of the lattice rectum. We're going to do the same thing here. Start at the vertex and curve toward the top of the minor axis. So that right as you're getting there, it's right as you get there, notice it's almost coming in perfectly straight, right at the very end, but just barely. Right? We'll do the same thing here. So right at the end, it's pretty much coming in straight. And then come around like that. My hand covers the R, so it makes it really hard to see. And there we get our ellipse, very nicely, neatly drawn. Okay, and it's nice because we got lots of points, right? We've got 1, 2, 3, 4, 5, 6, 7, 8 different points to help us draw our ellipse, which is good because it's really hard to draw an ellipse if you don't have all those points. But there we go. There's our ellipse. Questions now that you've seen one done, and now we'll do a few together. Any questions? All right, turn your textbooks, if you would, to page 245. Page 245. Let's take a look at number 1, letter C. Number 1C on page 245. Read the equation, if you would, please, Quentin.
X squared plus 4y squared equals 4.
X squared plus 4y squared equals 4. All right. The key to getting the elliptical form is to set the equation equal to... To do that, we need to divide everything by 4. And when I do, what does my equation become, Jade?
X squared over 4 plus y squared equals 1.
And for sake of the form, since I need a denominator, I'm going to go ahead and leave it over a 1. The center, again, for now is going to be at 0, 0. Which axis is major here, class?
X.
The x, whichever one has the bigger number underneath it. The bigger number's under the x-axis is major. So again, this ellipse is going to be wider than it is tall. The major axis's length hinges upon the denominator that we were just referencing. But again, this is a squared. So what is a, class? 2. So how long is the entire major axis? 4, or we could say 2 each. 2 each side. The minor axis is here represented by the b squared. Well, if b squared is 1, then b is
1.
So how long is the minor axis? 2. Or we could say 1 in each direction. For the focal length, we need to take the square root of the a squared minus the b squared. So you take the actual denominators, subtract them, and take the square root to get an irrational value. Square root of 3, so approximately, what is that from your calculators?
1.8732.
Yeah, about 1.7. All right. And then for the half latera recta, we're going to take the b squared value and divide it by the a. Well, you can do that in your head. What do we get? 1/2, or 0.5 if you want to go with the decimal. you can use the Cartesian plane from your homework where you have that circle drawn. And let's go ahead and graph this together. Let's graph this together. Of course, our center point is going to be at 0, 0. And along the x-axis, we're going to go 2 in each direction. Along the other axis, we're going to go 1 in each direction. So that would be the y-axis. Go up 1 and down 1. Okay, it's kind of on the small side, so it's hard to label. I think I might take my little c off of here. But we see our center, our vertices, and these don't have names, but they're the ends of the minor axis. The focal length here is 1.7. So we're going to go all the way out 1.7, which is really close to our vertices. Okay, so this is a higher eccentricity. This is about, oh goodness, if we took this, this is a 0.86, 0.87 eccentricity. It's higher eccentricity than the last one, which means less circular. And through the foci, we're going to go up and down a half, right? That goes perpendicular to our major axis. So we'll up a half, down a half, up a half, and down a half. Zoom in just a little bit here. Make it a little bit easier to see. And then start at the vertex, curve to the ends like that. I want to kind of retrace the whole thing just to make it look nice and uniform. And there we get our ellipse. It almost looks like an eye now, doesn't it? Little eyelashes on there. And shade in the ellipse. Put some red vein lines in there for bloodshot seniors' eyes from all the studying you've had to do lately. Anyway, like little tears coming out. Slowly dripping down your face. All right. Anyway, artwork. Our modern art. There we go. Questions on this? The key again is to not make it look like a football. Again, we can't go straight line. We don't want it to come like where it's got a hard V. Okay, it's got to still have a curve to it. So make sure it's curved and not, football end looking. But there we go. Questions on that? I was hoping we'd have a little bit more time, but it looks like we are out of time for this. So I'm going to have you try 2 of these. Let's see how we do with them. And that is page 245, number 1, A and G. Page 245, number 1, A and G. You may be able to do these on the same graph grid. Okay, if you want to do them separate, that's fine, but I'm okay with you trying these on the same Cartesian plane. We'll take a look at these tomorrow, and then tomorrow just more practice with these ellipses. Start to get the shape down really well, and get the math down really well also. All right, when the bell rings, you'll be dismissed. Have a wonderful rest of your day.